Hello.
Yes, sir.
Okay.
You're audible,
Yes,
sir.
sir, you're audible.
Screen visible?
Yes, sir.
So if there are any questions and doubts, you can ask. Anybody?
Sir, last class we did that Rayleigh proportional damping model. No? So there, phi I transpose C into phi I we have written as 2 into xi into omega ni. So that how did we write, sir? The left hand side.
So we are actually assuming. We have not given that proof, but that is how it comes. No, if the phi I is normalized with respect to mass matrix, so then this phi I it is like a single degree of freedom system. So if you have the damping term there, so that gets converted into 2 xi into omega n, phi transpose into C into phi. Yeah, so I have not given you the proof for that. Yeah.
Okay, sir.
Yeah, but it is analogous to single degree of freedom system. No, the whole thing you divide by m and then write it, so you get 2 zeta omega n there. So say same logic is applicable here.
Okay, sir.
Any other question, anybody? Okay, so let me start then. So today
So what is the procedure that we should follow to solve the damping problem? Like we should know the natural frequency first to find out the alpha and beta.
Okay. We should know the natural frequency, and we should know the damping factor in two modes and the basically corresponding natural frequencies. So natural frequencies you can also determine experimentally or through the model in algorithm itself. Yes. Okay.
Yes.
Okay. Anybody? Any other question?
Sir, can there be a case like our viscoelasticity kind of study what we did? So the material nature is viscoelastic, and we are doing dynamics problem with that material. Then damping from both the problems we have to consider, like.
No, then if you have viscoelastic constitutive modeling, and you can have both, but usually if you have viscoelastic constitutive model, then you need not incorporate this separately damping. Of course, one can have both, that is also possible, but usually if that viscoelastic damping is there, then you need not include this. Yeah, but if that is a material damping and you have other damping effects, then you can have both. Yeah. So let me then start. So today what I will do is I'm going to discuss time integration techniques, how to do the dynamic integration, basically the direct time integration of the equations of motions. Yeah, is the screen visible?
Yes, sir.
Okay. So now continuing with the dynamics. So I think in dynamics, of course, whatever you learn in mechanical vibrations or structural dynamics course for multi-degree of freedom systems, so all those things, tools and techniques are applicable. I'm just discussing this only the time integration technique. So if you are having the equation of motion, the force here as a function of time is given and the initial conditions are given, how to get the dynamic response. So that is what I will discuss today. So that is direct time integration techniques, and I'm going to discuss just two techniques, one from the explicit example and one from the implicit. So we know that the equation of motion we already know, that equation of motion after assembly and imposition of boundary conditions. So we know this m into d double dot plus c into d dot plus k into d is equal to f. So this equation is no, we know once we get so the role of finite element is just to get this equation, and then now in the time domain you want to solve this. So you have this at 0. So at 0 time, you know the initial conditions, and then you want to solve for delta t, 2 delta t, 3 delta t. So like that you want to solve this equation somewhere then t, and once you know the solution at t, you want to solve it for t plus delta t. So for doing this, there are two techniques, two broad techniques. One is the explicit time integration techniques, and the other is the implicit time integration techniques. So under I will discuss one technique under each of these. So in case of explicit time integration technique, main thing is that solution we want, we have got the solution say up to t, and then we want to get the solution for t plus delta t. So what we do is, in this case, solution at t plus delta t is obtained from equation of motion at t. So when we want to find out the solution at t plus delta t, we write the equation of motion at time t plus delta t. So that means we assuming that of course here although for nonlinear problems you might have stiffness as a function of the unknown vector d itself in a nonlinear problem. So the treatment is same. So let me write that equation. So in this case, what it means is that when I say this, so that means what we are writing m into d, and now d double dot at time t, because we are considering the equation of motion at time t to find out the solution at t plus delta t. So m into d double dot at t plus c into d dot at t plus k into d at t is equal to f at t. So yeah, this is what we do. So the main thing in the explicit time integration is that solution at t plus delta t is obtained from equation of motion at t, that is using basically this equation of motion. And of course here you know that d is a function of time, so d is d double dot d dot are considered at time t in the equation of motion. So now how do we do this? So now this is the equation of motion at t. Now we want to introduce d at t plus delta t. So how do we do that? That is through the d double dot and d dot, using this explicit technique. So now under this category, I'm going to discuss the central difference method. So most commonly used method is central difference. Central difference method under this explicit category. So now in this, what you do is now that is what I am saying. Know that you have, let us say, t minus delta t and t, and then t plus delta t. So these are the time instances, and this both sides you have there. So now when you want to write, in the equation of motion, you have to replace this d dot at t and d double dot at t. So using central difference, we write d dot at t using central difference. So that is written as basically 1 upon the difference of d at t plus delta t minus d at t plus delta t, and divided by the time interval. So the time interval here is 2 delta t. So this is 1 upon 2 delta t into d at t plus delta t minus d at t minus delta t. So this is how we write d dot using central difference. So if you want to write d dot at t, you just take the difference of d at t plus delta t and d at t minus delta t and divide by the time interval. So this time interval is delta t, this is interval is delta t, so total is 2 delta t. And then you write this d double dot at t, again using central difference. So what you can actually do is take the intermediate time steps here and here. So that would be 1 upon delta t. Then you can write d dot at t plus delta t by 2 minus d dot at t minus delta t by 2. So, and then we want to finally write it in terms of basically the d. So that is 1 upon delta t, and then this we write d dot at t plus delta t as d at t plus delta t minus d at t divided by delta t, and minus similarly d at t minus delta t, we write d at t minus d at t minus delta t divided by delta t. So you can write this as you see 1 upon delta t square, and then we have d at t plus delta t minus 2 at d at t, and plus we will have d at t minus delta t. So this is what you get as d double dot at t. And now substitute these in the equation of motion. So that is this equation of motion, what we have here. So we substitute in this equation of motion and get actually the equation to find out d at t plus delta t. So substituting d double dot at t and d dot at t in the equation of motion, at t. So what we will actually get is, as you see, we will have m into then d double dot at t, which is 1 upon delta t square, and that is
So while taking that dt dot, we use time interval 2t, but while taking its double derivative, why we are doing in this way? Why not in the same way, like d dot of at t plus delta t minus d dot at t minus delta t and whole divided by twice of delta t?
So that involves more the solution at other previous steps. So that will be when we start this, then you need the solution at minus delta t minus 2 delta t, which is not possible to get. So best way is to write this d double dot in this manner, in terms of values of central second derivative in central difference is written in terms of these values at t plus delta t, t and t minus delta t. If the way you are saying, then it will be in terms of d at t minus 2 delta t and so on, and that will be difficult to get at the initial time when we start, because we will not know the solution at d at minus 2 delta t.
So can we arrive at the conclusion that when the derivative increases, we have to go more close to the t time, like the current time?
Yes. So basically in the central difference, the second derivative is written like this, the way it is written here, this one. Just to show you how do we get this, I have just written this step. Otherwise, no, this is what we do. Okay. So yeah, okay. So this is now when you put the values, so you get d at t minus delta t. So this is with m, and then we have c and 1 upon 2 delta t, and then we have d at t plus delta t minus d at t minus delta t. And then we'll have of course this k term, so k into d at t is equal to f at t. So now if you see the unknown, we want to find out because we would know all the solutions up to t. So we want to find out the d at t plus delta t. So this is one term in terms of that unknown, and this is another term. So we keep these on the left hand side and take all the other known quantities to the right hand side. So we can write this equation as 1 upon delta t square into m plus 1 upon 2 delta t into c, and this whole thing into d at t plus delta t is equal to right hand side, rest of all the terms now you take to the right hand side. So f at t minus this k term will be there, so k into d at t, and then you have from the mass matrix term we will have m into 1 upon delta t square into 2 dt minus d at t minus delta t, and plus c into 1 upon 2 delta t into d at t minus delta t. So this is the equation you get. And so now if you know the solution at time t, you can get the right hand side, and then you can solve for d at t plus delta t using this equation. So that is how you do in central difference. Now even with this, when you see at starting time, when we have solution at t equal to 0 and we want to get the solution at basically delta t equal to delta t. So then in the equation here, if you see t equal to 0, so you will have d at minus delta t, So how do we get that? So there is a starting difficulty in central difference technique. So at the start of the integration, so that is when we are considering the equation of motion at t equal to 0. So we know initial conditions. The initial conditions are, that is we will know d naught, that has to be given. We know d naught dot, that is d dot at this, and we can calculate from the equation of motion at t equal to 0, we can calculate d naught double dot. So that means this is calculated from the equation of motion at t equal to 0. So because d naught and d naught dot are known, so no, you just get the d naught double dot. So once this is calculated, so how do we get then d at minus delta t? So to get that, now if you consider these relations, central difference, so d naught dot t equal to 0, d naught dot would be 1 upon 2 delta t, and then will be d at delta t minus d at minus delta t. So this is one equation, and another equation would be d naught double dot. So d naught double dot is 1 upon delta t square, and then d at delta t minus 2 at d naught and plus d at minus delta t. Same relations what we have written. So now if you solve for d at minus delta t, so that solution you will get d at minus delta t if you solve these two equations, because we know this d naught dot we know, d naught dot we know, d naught double dot we know. So we can, from this equation, we can solve for basically d minus delta t. So d minus delta t, you solve for d minus delta t, and after the solution you will get the d minus delta t will be equal to d naught minus delta t into d naught dot and plus delta t square by 2 into d naught double dot. So that means at the starting of the integration, we know the initial conditions d naught dot, we calculate d naught double dot from equation of motion at t equal to 0, and then from this relationship we get d at minus delta t using this relationship. And once we have this, then we can get the solution at delta t, at d at delta t using this. And once we have got the solution at d at delta t, then we go for the next step. That is, we go for 2 delta t. So for finding out the solution at 2 delta t, we consider the equation of motion at delta t and then continue this procedure. So this is how you solve this. So the whole solution procedure is like this. Now one of the one advantage you would see in the explicit technique, because the equation of motion is considered at time t for finding out the solution at t plus delta t. So even if it is a non-linear problem, if it is non-linear problem, either material non-linearity or geometric non-linearity, any kind of non-linearity, this k will be function of d. But since the equation of motion is considered at time t, so for that instant the solution dt is known, so you can get this k. So there is no difficulty in handling non-linearities in explicit technique. So that's the one advantage. Another advantage I'm going to discuss in terms of computational time. So yeah, suppose we have undamped system. So suppose we have undamped system. So for undamped system, you will have this equation where c is 0 in the undamped system. You will have 1 upon delta t square into m into d at t plus delta t, and the other terms on the right hand side, f at t, the force full load vector, minus k into d at t plus 1 upon delta t square into m into, I know here you will have 2 dt minus d at t minus delta t. So this is the equation, and we use diagonal mass matrix. So for example, if you use lumped mass matrix, so m would be diagonal, and if m is diagonal, then you don't need the solution of simultaneous equation. For each degree of freedom you can write the solution directly. So computationally, because in finite element analysis most of the time actually is spent on solving the simultaneous equations, but here you can avoid that if you use diagonal mass matrix. So if we use diagonal mass matrix, then we do not need to solve simultaneous, we do not need to solve simultaneous equations together. So that is because if M is mass matrix is diagonal, so for example you use lumped mass matrix, or from consistent mass matrix you derive the diagonal mass matrix. So then the solution, say for the ith degree of freedom, so d at t plus delta t corresponding ith degree of freedom, I superscript I is the ith degree of freedom I am saying, can be directly written as 1 upon delta t square upon, so we will have here that just the diagonal mass matrix is say mi, and then into this side we will have f of t minus k into d of t and plus 1 upon delta t square into m into 2 dt minus d at t minus delta t. Yeah, so you can directly write it like this. So now you are no need of inverting a matrix. So that lever is saved if we use diagonal mass matrix. So here I denotes ith degree of freedom. So you can just use this equation to solve for the unknowns. So you are not inverting the matrix because it is already diagonal. So you can solve for each degree of freedom separately. So this is computationally very efficient. Computational time in inverting the matrix is saved. Computationally very efficient. Now another aspect.
Hello, sir.
Yeah.
Sir, on the right hand side, why don't we have that ith degree of freedom?
Yeah, right side also we have to take the ith degree of freedom. Yeah, so let me put a superscript I here. So right side also it is the ith force vector. You have to have that. Yeah, thanks for correcting this. So right hand side this I has to be there. So this is ith degree of freedom. Yes.
And so one more thing I wanted to ask, like we solved for d of minus delta t.
Yeah.
But the same equations can also be used, like there are two variables, right? D of delta t and d of minus delta t.
Yeah.
So d of delta t also we can calculate from there.
No, but then we also want to satisfy the equation of motion. So if you solve from there, you get d at so like that you can continue doing that, but then you don't bring in the equation of motion in that. So we want to bring in equation of motion for the solution of d at t plus delta t.
Okay.
So the equation of motion has to be satisfied. No, so for that you have to bring in the equation of motion.
Okay, so d of minus delta t is only a mathematical quantity, like.
Yeah, that's only a mathematical quantity because to start with we need that. So we one way is to calculate that way.
Okay.
Yeah. Yeah. So here now the next thing is in explicit techniques, the choice of delta t is very critical. So in explicit techniques are usually explicit techniques are conditionally stable. So the choice of delta t is very important from the stability point of view. So explicit time integration techniques are conditionally stable. Conditionally stable, and what does it mean is, now when we say it is conditionally stable, so that is for stable solution delta t has to be less than certain critical value, delta t critical, and usually this delta t critical is taken as Tn upon pi. So if now that means delta t has to be smaller than a certain critical value. Now if delta t is greater than not equal to, so if delta t is greater than delta t cr, delta t critical, we get, so if you continue integrating in the time domain, we get unbounded solution even if the actual solution is bounded. So that's the actually problem. So we have to have delta t smaller than a certain critical value, and that is usually taken as Tn upon pi. So now next question is, how do we get Tn? So this Tn is the smallest time period of finite element assembly. The smallest time period means corresponding to highest natural frequency. So smallest time period of finite, whatever mesh and assembly we are using finitely after imposing the boundary conditions. So for that, whatever is the highest time period, so you know that means this Tn can be written in terms of the highest natural frequency. So that would be 2 pi by omega n maximum natural frequency. So now if Tn is this, so then you can say that delta T critical would be 2 upon omega n max. So that is how you write the delta T critical. Now, but the difficulty is that we usually, when we solve the eigenvalue problem, we try to find out first few smaller natural frequencies. So how do we estimate the highest natural frequency? For estimating the highest natural frequency, one simpler approach is that we approximate this omega n max, we take approximately as the maximum over all elements. So for each element, we find the natural frequency, that is omega n max for the element, and over all the elements, whichever gives maximum, we approximate it like this. So now here omega n max E is the maximum over is the maximum frequency of eth element. Maximum frequency of eth element. So we know that means for this what we do is we solve the element level eigenvalue problem directly without assembly and boundary conditions. So we will have, say, Ke dE is equal to, we solve this omega n E square into me. We solve this eigenvalue into dE. So we solve this eigenvalue problem, get the highest natural frequency, because the degrees of freedom for the element are smaller. So it is easier to solve for the eigenvalues, then get the omega ne max, and then find out this over all the elements and get this omega ne max, that is this, and then you have get the delta T critical, and then you use delta T which is equal to or smaller than this delta T critical, and solve the problem. So this is how and many often in the wave propagation problem, suppose you are wanting to solve a wave propagation problem. So let us say this is a rod and some force is applied over here, say in this direction, and then the wave is traveling through this medium. So let us say in this the wave speed is c. The c is the wave speed, and which is equal to, for one dimensional problem, it is square root of E by rho. So this is small c, not the damping matrix. C is the wave speed. So this is a square root of E by rho. And in that case, you choose now have the element size. So you choose it based on the now you have discretized into number of elements. And let us say the smallest element edge length is h, smallest element edge length. So in that case, you take this as h upon c as the delta T critical. No, rather delta T, not the critical actually. Delta T you take as h upon c for wave propagation problems. So in the explicit technique, so that's one way of you have some guidance, and of course you need to do so. Usually in the explicit techniques, the delta T is governed by stability, and because it is usually much smaller, so the solution will be accurate. So that is how you handle this delta t in case of explicit techniques. Now sometimes what is also done, yeah. Yes, please.
So just like you told about the for rod delta T is H upon C. So similarly for the beam also we can we say H upon C for delta T for the beam also?
Yeah, so in that case you have to take the speed of flexural waves. Yeah, but you can, yes, you can do in a similar manner, yes.
Okay, so that their C will be different, will be a component
yeah,
of
yes, flexural wave speed.
Okay, thank you.
Yeah.
Hello, sir.
Yeah.
Sir, like when calculating that omega n max E, so
yeah,
we solve the eigenvalue problem at the element level, right?
Yeah, this eigenvalue problem, yes.
So that is without imposition of boundary conditions.
Yeah, this is without imposition of boundary conditions, yes.
So then, like while calculating this delta t critical, boundary conditions will not come in picture.
Yeah, but usually you find that the omega, the omega n max will be smaller than or equal to omega n max E. That is without any boundary conditions, because the highest natural frequency of each element will be actually either more than or equal to omega n max. So that is the property we use to find out this omega n max through this approach. And if you want to see the proof for that, you can refer to this finite element procedures by K.J. Patel. So in that you can find this proof that no omega n max will be less than equal to omega n max E.
Okay, sir.
Yeah. Now another important thing you find that these explicit techniques are also used actually not only for the dynamics problem, but they are also used for statics problems. So if you see in the commercial packages like Abacus explicit or LS Dyna, or you see the ANSYS Autodyna. So you will find that these explicit techniques are also used for solving the statics problem. So they are converted actually into a dynamics problem, but the loading is applied slowly so that the dynamic effects are minimal. The effect of dynamic terms in the solution is minimal, and from that you can solve. The advantage is that you don't have to solve, use the diagonal mass matrix, so you don't have to solve the simultaneous equations, and you get the solution computationally very easily. Computationally you get the fast solution faster. So that these techniques are also used in that. So that is in commercial packages, or you can write even your own code. So in commercial FE packages, explicit techniques are also used to solve nonlinear statics problems, equilibrium problems. Only thing is now you will assume that rather than the total force applied at once, the total force is applied gradually, but it is so gradual that the dynamic effects are the induced dynamic effects are minimal. So you have this and time t over here. So if we have a force, now you apply it gradually increasing like this. So this you apply over a time interval, say t, in this time interval t, and this t must be greater than t max. T max is what? T max is the largest time period of finite element assembly. Means it would be corresponding to lowest frequency. which is easily, you solve the eigenvalue problem, get the lowest natural frequency, and 2 pi by that lowest natural frequency will give you this T max. So here we keep the T max actually no greater than T max, and usually to make sure that the dynamic effects are not induced, T is taken as 10 times of the T max. And solve this problem in this manner as a dynamic problem. So at the end of at T equal to capital T, whatever solution you get is the solution of static problem corresponding to the total force. So that is how you solve the statics problems also, particularly nonlinear problems using this explicit integration techniques. Now because this T is large, capital T is 10 times of T max itself is large. So you'll have to do the integration over a larger time period. So and delta T is, because it is explicit technique, so delta T would be governed by the stability condition that delta T has to be less than delta T critical, and which is in terms of the smallest time period. So now that means you could end up solving the equations, although simultaneous equations solution is not involved. But you have to evaluate the matrices and everything, the matrix vector products at so many steps that again it might become computationally more involved. So for that, what you do is you also do something known as mass scaling. So to reduce the computational time further, mass scaling is done. So if you do the mass scaling, that means you actually increase the mass, so the highest natural frequency will come down. So when your highest natural frequency is coming down, you can have basically larger delta T, so that you need to solve at lesser number of time instances. Mass scaling is used. So there are different ways of mass scaling. I'm not going to discuss that, but to reduce the computational time further, mass scaling is used. Yeah, so this is what I wanted to discuss in the explicit time integration techniques. Yeah.
So what is mass scaling basically?
No, I think please repeat again. Your voice was not clear.
Sir, I'm saying, sir, what is mass scaling basically?
Mass scaling is increasing the mass. Increasing the mass of the system. Yeah. Mass scaling is increasing the mass, so that increasing the mass such a way that highest natural frequency comes down, so the delta T critical will increase, so that you need to solve from 0 to capital T. The number of solution steps would be reduced, and so that the computational time will be further reduced. So mass scaling means increasing the mass such a way that the highest natural frequency comes down.
Sir, but sometimes how do we know whether the solution is correct or not, sir? Because once we do the mass scaling, we can use any numbers. So
now I am talking about this for solving statics problem. So and now you also look at the kinetic energy. So when you look at the kinetic energy in the solution, so if kinetic energy is, let's say, less than 10%, or for you can keep a range between 5 to 10%. So if the kinetic energy is less than say 10% or 5%, whatever, depending on what criteria you want to use, if the kinetic energy is less than that, then you can say that the solution is a solution of a corresponding statics problem. No, but if the kinetic energy contribution compared to the total energy is higher, then the solution may not be accurate static solution. But if the contribution of kinetic energy is say 10% of the total energy, then you can say that the solution is fairly accurate solution of the corresponding statics problem.
Basically, total internal energy, no, sir. We have to compare kinetic energy to the
you have to take the strain energy plus the kinetic energy. That is, I'm saying total energy. So the kinetic energy should be just 10% of that total energy.
Okay. And when this mass scaling is done, sir, we use again the lumped mass matrix only, and the diagonal elements
you have to use lumped mass matrix, because that is where we get the advantage in terms of solution. No, otherwise, if we are not using lumped mass matrix, then we have to solve the simultaneous equation, and which is time consuming. So we will not get the advantage in terms of computational time if we are not using lumped mass matrix. So we have to use lumped mass matrix.
Yeah, and the scaling of mass also is done in terms of diagonal elements of that lumped mass.
Right. Yes, right.
Okay, sir. Got it. Thank you.
Okay. So now the next is I'm going to discuss is the implicit time integration techniques.
Hello.
Yeah.
Sir, so is this concept a theoretical one, or like are we actually will be going to increase the mass?
So it is in the model you are doing. No? In the finite element model, you have the diagonal mass matrix and you are increasing that mass. So it is in the computational model. No, this is I am talking about. See, this part is for the statics problem. No, from this onward, this is applicable to statics problem. So we want to use the explicit technique for solving the statics problem. So for that I am saying, because you have to apply the load over the T max, 10 times of T max. So the time interval is quite large, and delta T has to be small, because it has to be less than equal to T delta T critical. So the number of steps would be large. So although the solution of simultaneous equation is not required, but you are evaluating the stiffness matrices of all the elements every time and doing the multiplication assembly and then multiplication of matrices and vectors. So that itself would be large. So to reduce that time, computational time, you use this mass scaling. So this is it is not that in the structure you are doing something. The structure what you are modeling is as it is, but in the numerical finite element model, you are scaling. You are multiplying the diagonal mass matrix by a certain factor, so that the highest natural frequency comes down, and therefore delta T critical increases. So you have lesser number of time steps here, and so that the solution can be faster when you are doing the solution over here. Okay?
Yes, sir.
So then let me now then start this implicit time integration techniques. Implicit time integration technique means as against the explicit, the solution here, the solution at T plus delta T is obtained from equation of motion at T plus delta T itself. Equation of motion at T plus delta T. In the earlier case, in the explicit, the solution at T plus delta T is obtained from equation of motion at T, but in implicit, the equation of motion is considered at time T plus delta T itself. And one of the most common used implicit technique is Newmark's average acceleration method. So in the Newmark, as I said, Newmark's average acceleration method, that's the most commonly used. There are other methods like Wilson theta, Hobart, the linear acceleration. So there are different methods, but most commonly used is this. And in this technique, what we do is to get the solution at T plus delta T, we consider the equation of motion at T plus delta T itself. That is, we consider M into D double dot at T plus delta T plus C into D dot at T plus delta T plus K into D at T plus delta T is equal to F at T plus delta T. So we solve this equation like this. You remember in explicit it is written at time T. So now in the Newmark's, as I said, it's an average acceleration approach. So in this, now if you look at the acceleration acceleration here and time here. So let us say we have time t and then t plus delta t. We would have solved the problem up to t and then we want to get the solution at t. So let us say at t you have some acceleration. This is the acceleration at t. So this is d double dot at t, and then at t plus delta t you have another acceleration. So let us say that is d double dot at t plus delta t. So between these two we take the average acceleration. So this average acceleration, this is taken as half of d dot at t plus d double dot at t plus delta t. So that's the average acceleration we take. And now again, because we are solving this problem as a discrete problem, so now you have to have the additional equations. So they know you need to write d dot at t plus delta t in terms of d at t plus delta t, and similarly d double dot at t plus delta t in terms of d at t plus delta t. So you need to do that. So now we make use of the concept of average acceleration. So from acceleration we can write velocity. So I can say d dot at t plus delta t can be written as you write the velocity v equal to u plus at. U is the v is the final velocity, u is the initial velocity, a is the acceleration, t is the time interval. So now we know the solution at t. We want to write d dot at t plus delta t. So that is the velocity will be initial velocity is d dot at t and plus now the delta t into acceleration. Acceleration is average acceleration, so that we will get the time is delta t and half is coming from the average acceleration. So we will have average acceleration as d double dot at t plus d double dot at t plus delta t by 2 is that's the average acceleration into delta t gives you the velocity. So this is like v is equal to u plus at. If you remember in the simple dynamics, engineering mechanics, rigid body dynamics, we write v equal to u plus at. So this is like v and this is like u, and half of d double dot at t plus d double dot at t plus delta t is like a. This and this together is a and into delta t. So that gives you the d dot at t plus delta t. Then we write using this same concept, we also write d at t plus delta t. So d at t plus delta t can be written as, now that is s is equal to that ut plus half of at square and plus the initial displacement. So we will have initial displacement d at t plus we will have u into t. So t is interval is delta t into d dot at t, that is ut plus half at square, and that half at square would be delta t square by 4. So one half coming from the average acceleration, another half coming from the equation of motion. So you get here d double dot at t plus d double dot at t plus delta t. So now what you can do is actually using these equations we want to express d double dot at t plus delta t and d dot at t plus delta t in terms of d at t plus delta t, and then we substitute that in the equation of motion and solve for d at t plus delta t. So from this equation itself, the second equation what I have written, you can write d double dot at t plus delta t is equal to, now you take this on the one side, this term, and all other terms onto the other side. So you can write that as, you can see it can be written as 4 upon delta t square into d at t plus delta t minus d at t plus you will have 2 upon delta t into d at d dot at t 2 upon, this is 4 upon delta t square. Yeah, this is 4. This is 4 upon delta t. I think, yeah, let me correct it. This is also. So now from this equation we will get d double dot at t plus delta t is equal to 4 upon delta t square d at t plus delta t minus d at t minus 4 upon delta t into d dot at t minus we will have d double dot at t. So now we have expressed d double dot at t plus delta t in terms of this unknown. These will be known because these are the values corresponding to the previous time step. They are all known. So this is known. And similarly, you can write now once you have got d double dot. So in this equation, you can put d double dot at t plus delta t and then solve for d dot at t plus delta t. So similarly, from then this equation you will get, I am writing the end result. You can see that now the steps involved yourself. So d at dot at t plus delta t would be equal to 2 upon delta t into d at t plus delta t minus d at t minus you will have d dot t. So this is what you get as d dot at t plus delta t. Now we substitute this in the equation of motion. So substituting d double dot at t plus delta t and d dot at t plus delta t in the equation of motion at t plus delta t. So what do we get? So let's see that. So if you do this, now in the first term is m into d double dot at t plus delta t. So we will have m and into we have got this expression for, so that is 4 upon delta t square. And then you have, yeah, let me put the small bracket, although these are vectors, d at t plus delta t minus d at t minus 4 upon delta t into d dot at t minus the d double dot at t plus you will have c into d dot at t plus delta t, that is also written as 2 upon delta t into d at t plus delta t minus d at t minus d dot at t. So this plus of course now k. So if it is a non-linear problem, this k, no, k, if it is a non-linear problem, then it would be function of d at t plus delta t, and d at t plus delta t is an unknown. So that will create of course the problem. So but we will have k into d at t plus delta t is equal to f at t plus delta t. So this is how the equation of motion will be after substituting these. So now you can see, you can rewrite this equation as taking all the unknowns on the left hand side and all the known quantities on the right hand side. We can now look at this equation. We can rewrite this equation as 4 upon delta t square into m plus 2 upon delta t into c plus k. Now the k term is on the left hand side, you see, into d at t plus delta t. So this is what is there on the left hand side is equal to, we will have f at t plus delta t and we will have plus the other terms coming from the inertia term. So m into 4 upon delta t square into d at t plus 4 upon delta t into d dot at t plus d double dot at t. So this m term and plus we will have c into 2 upon delta t into d at t plus d dot at t. So now this equation, so now what you see is now we know the solution. So how the solution will proceed in this case is you will start t equal to 0, you will know all the initial conditions, then you will go for delta t, 2 delta t and 3 delta t and so on. So you'll solve for the delta t, then from there you will go to 2 delta t, and like that you will get the solution at t, and then once you have solution at t, you can go for the solution at t plus delta t. You will see that in this case there would be no starting issue because we require the solution at t plus delta t is in terms of just the values of various displacement, velocity and acceleration at time t. So those quantities at t equal to 0 you already know. You will know d naught and d naught dot, and you will be able to calculate d naught double dot that is at t equal to 0 from the equation of motion at t equal to 0, and then you solve for the the solution at delta t, 2 delta t and so on. You know the solution up to t, and then you get the solution at t plus delta t. But now the difficulty you will see, because no mass matrix can be diagonalized and sometimes the damping may be absent. But in this case, even if you use the diagonal mass matrix and if the damping is absent, now this K is there on the left hand side in the coefficient matrix, and K cannot be diagonalized because the restoring forces have to be represented correctly, and for correct representation of restoring force we will have to use K as it is. K cannot be diagonalized. So if K cannot be diagonalized, then you have to always solve this set of simultaneous equations. That means you have to invert this effective stiffness matrix, which is 4 upon delta T square into M plus 2 upon delta T into C plus K, has to be inverted, and that takes a lot of time. So that this technique is computationally very involved in terms of the solution of simultaneous equation because of the presence of K over here on the left hand side in the coefficient matrix. But the advantage of this is that delta T is then can be chosen based on accuracy. So the implicit techniques are unconditionally stable. Implicit techniques are unconditionally stable. That means you can choose any delta T. It will give you the stable solution, although that may not be accurate. For accuracy, you have to have the sufficiently smaller delta T, but that usually turns out to be much larger compared to delta T critical in explicit techniques. So the number of steps for going up to a certain time interval is actually less. So no, we can solve this equation easily without worrying about what delta T we should take from the stability point of view. Although from accuracy point of view, you have to choose a smaller delta T. But from this from the accuracy point of view, of course, you have to choose the appropriate delta T. So now if if it is a nonlinear problem, linear problem, it is straightforward. No, you get this K and give this effective matrix and then invert it once and then continue using the same thing. Yeah, yes, please.
Sir, for the same efficiency, which technique is more computationally efficient?
As I said, typically for the nonlinear problems, actually you use this and particularly nonlinear problems, high strain rate deformations and impact problems where the total time duration for solution is smaller, you go for explicit technique, central difference method. But if you are solving structural dynamics problem, so in case of structural dynamics problems, you are interested in solving the problem for a much larger time interval. So if you are solving for a larger time interval in case of structural dynamics, then you use implicit technique because the advantage is time is more. You can have larger delta T because delta T is just governed by only accuracy. So you can use larger delta T and solve it. So for structural dynamics, you usually use this implicit techniques like Nemack's average acceleration technique, and for high deformation rate problems, which are small duration problems, there you use explicit techniques like central difference method. So
it depends upon the time interval.
Yeah, it is dependent on the time interval of the phenomena. So now let me talk of how to choose delta T. Of course, as I said, if it is a nonlinear problem, then further if K is a function of D, then you have to solve this equation further using Newton-Raphson method. So like we have, in the plasticity, I was discussing how to use Newton-Raphson method. So similarly, we'll have to use Newton-Raphson method to solve this equation if problem is a nonlinear problem, that is if K is a function of D. If it is a linear, then it is straightforward, but for nonlinear problems, further in this, you have the equation in this form and then you have to employ this Newton-Raphson method to solve this for nonlinear cases. So that's the additional thing you need to do for solving this. So now you are just talking about, I just wanted to talk of choice of delta T. So how do you choose that? So choice of delta t is governed by accuracy, not the stability, because it is unconditionally stable, as I already said. So how do we get that? So for accuracy point of view, usually what you can do is you know, if you have an idea that how many modes are going to get excited, so whatever is the highest mode which will get excited because of the forcing function, so in the time in the period of that highest frequency, you should have about 20 points. So if you have that idea that what is the highest mode which is going to participate, the natural frequency of that, then find out the time period and take delta t, that time period divided by 20. So that is how you can do that. But if you don't have an idea, then another way is that you do the FFT, fast Fourier transform of your forcing function ft, and then find highest frequency, find the highest frequency content, highest frequency corresponding to, so let me write corresponding to significant amplitude. And then once you do that, so then you choose your delta t as 2 pi divided by 2 pi by omega max is the time period, divided by 20 is that you want to have 20 basically the divisions within one cycle. And we expect that if the highest frequency is omega max, so maybe 3 or 4 times of that will be the excited natural frequency of the mode, so you put a factor 4 also. So this is how you decide your delta t. So this is one approximate way of finding out the delta t. So you take delta t like this. If you directly know what is the highest mode participation, then you can simply take 2 pi by omega max into 20. But this omega max is the highest frequency of the forcing function. So omega max over here, you can get it like this. Then subsequently, you also might have to do the convergence study. So then that means you take this delta t, solve the problem, plot the displacement versus time, and then take half of the delta t, again do the integration up to that time interval, and then plot the two. If the two are matching, then you can say that this delta t is accurate enough. Then also do the convergence study. Now this convergence study is in terms of delta t. Other convergence study is in terms of the mesh. So that is one, and another is in terms of basically this. So now how do we? Yeah. So the other convergence is from one convergence is with respect to delta t, and another convergence is with respect to mesh. So for dynamics problem, so because you are doing the integration in time domain, so how do we choose the mesh? So particularly for structural dynamics problem, the choice of mesh how you choose is let me explain. So now the basic thing is that one should use fine enough mesh to accurately represent the highest participating mode. So how can you ensure this? That what mesh is to be used? See, because now in dynamics problem, when you want to do the time integration, that is more time consuming than the corresponding solution of eigenvalue problem. So actually for this, you depend on the eigenvalue analysis. So to decide this, that the mesh is fine enough to represent the highest participating mode in the dynamic response, to decide the above, you do the following. That is number one, do the modal analysis, free vibration analysis. So before doing the this dynamic response analysis, do the modal analysis. That is, solve the eigenvalue problem. Do the modal analysis, not model, modal. That is eigenvalue analysis. that is eigenvalue analysis. So when you do this, you get certain frequencies and mode shapes. So then you look for the modes with free vibration frequency up to omega max. Omega max is the highest frequency of the forcing function corresponding to significant amplitude. So I have already introduced omega max. Let me put F. F is for the forcing function. So now once you do this, so now you know that which is the mode which would participate in the response. And then refine, you have to now refine the mesh such a way that the natural frequency up to omega max F do not change with further refinement or further decrease in the element size. And once so refine the mesh, do the modal analysis, refine the mesh, do the modal analysis, and ensure that the pre-vibration frequencies up to omega max F do not change with further mesh refinement. And use this mesh for the force response analysis. Force response analysis. So this is how do the mesh choice of the mesh. So because if you want to directly do the convergence study of mesh with respect through the force response analysis itself, that is very time consuming. So you do the eigenvalue analysis, find out certain number of modes, and look for the modes up to frequency which is equal to omega max F. In the forcing frequency FFT, whatever is the omega frequency corresponding to a significant amplitude. So you look for the frequencies up to that mode, and then you make sure you do the mesh refinement and do the eigenvalue analysis and make sure that the mesh you are using is correctly representing the modes up to omega max F, and then use that mesh for your force response analysis. That is for the time integration. The time integration you do based on that. So I think this is what I wanted to discuss. Now I want to stop here. If you have any questions and doubts, you can ask. Yeah, any questions, doubts?
Hello, sir.
Yeah.
Sir, like you told to do that FFT of the forcing function, right?
Yeah.
So, like, are you talking about like when the forcing function is given as a graph?
If it is given as a graph, you have to actually discretize that. Yeah, obviously you cannot do without discretizing it. So you have to discretize it, take the data in the discrete form, and then do its FFT. And if it is already a known function, then it is easier.
Okay, so if it is given only, then directly we can take.
Yeah.
Okay, sir. If it is a graph, then we need to discretize it.
Yeah, you need to discretize it, take that digital data, and do the FFT of that.
Okay, sir. So FFT is not for continuous things. It is only for
continuous things. You can, if it is, let's say, the force is already a sinusoidal force, so then you already know what is its frequency, and then you have to represent that many modes having natural frequency up to the forcing frequency correctly, and then use that mesh. And same way, you decide delta t.
Okay.
how do we deal with multiple
Yes.
frequency? Like suppose if force has multiple frequency, so it will
So,
simultaneously
you have to
like
take, you have to then actually take the highest frequency. You take the
Okay.
highest frequency that you use for finding out your delta t also, and also use that for finding out the appropriate mesh size.
Okay.
So highest frequency will choose in that case.
Okay. And sir, like, will this be valid for resonance condition also? Like if the forcing frequency.
It is valid for resonance also.
Okay, sir.
Yeah. So any other question? Anybody? Any other question? Doubt? Okay, so if there are no questions, I am stopping. Thank you all for your attention.